It is time for Module 5, Lesson 2. I'm afraid that this is not going to be quite as familiar for you as maybe the last lesson was, but nonetheless, it shouldn't be too super lengthy or anything. What we're looking at today is periodic trends. We talked about in Module 5, Lesson 1 about how the periodic table was arranged based on properties. So there are quite a few trends to the table, and we have to know those, so let's go at it. First of all, there's trends in atomic size and ion size. So I kind of lump these together and just look at it as just one thing, size, the size of the atoms, whether they're ions or not. An ion is an atom with a charge, and an atom is an atom with no charge. So, they're related to each other. First of all, I do want you to know the definition of atomic radius, because sometimes you'll see this as, let's see if I can find my mouse here. Oh, I'm writing all over the place. I found it. So here, there we go. Now, sometimes this will be referred to as like trends in atomic radius. So you might see a test question on the final exam or something in another class about atomic radius, the same thing as atomic size. The atomic radius is half the distance between the nuclei of two atoms of the same element when the atoms are joined. Now that sounds a little bit weird, but here's the thing. We've already learned that atoms are mostly empty space. So in essence, it's really hard to see like the electron clouds of the atom. It's easier to, you can find the nucleus, but it's like you really can't see everything outside of that. So if you put atoms next to each other, all you'll know is that you have a nucleus right here of one and a nucleus here of another, and that's all you'll see. So what they'll do is they'll measure the distance between the two and cut it in half, and then you assume that from there that there's, equal distance around for one atom and equal distance around for another atom, if that makes any sense whatsoever. They just, will assume that half the distance between two nuclei is where the outer edges of the atom is. So that is how you define atomic radius. That's how they find it. Now, apart from that, which looks like some eyeballs with glasses or something, the trend in general for size is this arrow, and this is how I teach my kids in class, is that atoms get bigger down and to the left. So I do all of my trends as arrows. If you look this up in textbooks, you are going to find some like really confusing things. The same thing online. You'll find people that tell you that atoms get smaller going up and bigger to the left, and then the next trend is going in different directions. If you'll do it the way I'm telling you to, you can boil this down to two arrows. This one is an arrow that goes down and to the left. It's biggest down here, and that means it would be the smallest up here. Now, why do I care that my arrow is going down and to the left? Because what that means is as you go down a group, the atoms get bigger. And as you go from left to right, no, I said that wrong. As you go from right to left across a group, they get bigger. So if I ask you some questions with this, and I think I just have my next trend on here. So if I ask you some questions with this, I would expect you to be able to tell me what atom is bigger or what atom is smaller. Okay, so I do actually have some practice problems on here in just a second. Let's go to this one really fast. Here's the definition of an ion. It was on the other screen, the word was, and I told you that it's an atom with a charge. It could also be a group of atoms with a charge. If you have a positively charged atom, then that is when you have a cation. And if you have a negatively charged electron, that is when you have an anion. You did this when you did the PhET simulation, and you played around with the number of electrons. And in that exact simulation, remember, if you had more protons than electrons, that meant you have more pluses than minuses. That made a positively charged atom. That's a positive ion. And if you had more electrons than protons, then you had a negatively charged atom. And what if they were equal to each other? If they were equal, if P's were equal to E's, then you ended up with a neutral atom. You have something with no charge. You do need to know, since we're talking about the periodic table, and this is going to be important moving forward for our next module, that metals lose electrons and nonmetals gain. Metals are losers. That means that if they lose electrons, that they'll have more protons than electrons. So metals are positively charged. And nonmetals, they tend to gain electrons. So that'll make them have more electrons than protons. So they'll typically be negative. Okay, so let's try a couple of problems here. Well, I swear I had these on there. Maybe I should go back and look. Let me put some practice problems in real fast. Okay, so here, I put us a periodic table in here. Let's look at size for just a second. So what if we have a selection of squares? What if I choose like these 4 squares right here and we look at size? Doesn't matter if it's size of the atom or size of the ion. If I ask you which one was the largest, if you have memorized your arrow goes this way, gets bigger down and to the left. So that means the biggest one is phosphorus, because I'm telling you arrows for the biggest of the trend, whatever trend it may be. So phosphorus would be the biggest. So phosphorus is the biggest. All right, so then who's the smallest? Well, that'd be oxygen. If biggest is down and to the left, then smallest will be up and to the right. So O is the smallest. What do we do with these two in the middle then? What about nitrogen and sulfur? Okay, very important here that its placement up and down is more important than left to right. Well, here's what I'm trying to tell you. Like nitrogen, it could be bigger, right? Because it's further left. But sulfur's further down. You see what I'm saying? Like this one wins the left-right battle, but this one wins the up-down battle. So which one's more important? Up and down is more important than left and right. So that means that sulfur wins. Sulfur's further down. Nitrogen's further left, but sulfur's further down, and being further down matters more than being further left. So sulfur would be the next biggest, and nitrogen would be, the next in line. Let's try this again. What if I choose these 4 right here? Now look, there are some exceptions to this. There's exceptions to pretty much all of chemistry. That is the only absolute about chemistry, is that there's always exceptions. I'm just teaching you the basic rules, and that's all I expect you to play by. All right, so let's arrange this group from smallest to largest. So who's the smallest? Well, our trend goes down and to the left. It's bigger down and left. So that means that iron is the smallest. So iron is the itty-bittiest of these. Okay, I also know the largest would be technetium. I don't remember what was underneath that. I think is it T? I think it's TC. Technetium. All right, so who comes in between? Well, manganese is further left. Rubidium is further down. That would make rubidium bigger than manganese. So rubidium should go here, and manganese would be the next smallest. Okay? Now, it's much easier on a test if I don't give them to you in a block. Like if I said cesium, vanadium, zinc, and neon. Out of those 4, which one is the biggest? Well, it'd have to be cesium. Why? Because it's the furthest to the left and it's the furthest down. So like it wins on all occasions. Probably the hardest one is the block of 4. Okay, our other trend. Our other trends, it's actually 2 trends, but our other arrow trend is ionization energy and electronegativity. You need to memorize the definitions of the words. The definitions are pretty straightforward. The words are huge, but the definitions are pretty easy. So ionization energy is how hard it is to take away an electron, and electronegativity is kind of like, sometimes too, by the way, this is referred to as electron affinity. So know it both ways. Electronegativity also equals electron affinity, and that makes more sense with the definition, is how it attracts electrons to itself. This trend, actually these trends, they get bigger up and to the right. It's the complete opposite of the other 2 trends, the size trends of atoms and ions. And we're going to learn in just a minute why these are backwards to each other. It actually does have something to do with each other, but it works the same way as what we were just doing. So if I skip over here to this and we look at, another block of 4, let's look at this block of 4 right here. Out of this block of 4, if I ask you who had the highest ionization energy, you just simply need to know that your trend goes up and to the right. So out of this block of 4, the one that is furthest up and furthest to the right would have the most whatever we're looking at. So if it's ionization energy, selenium has the most. Antimony would have the least. Now, how do you do this? If we're doing it in order of increasing, we said selenium would have the most and antimony would have the least out of this block of 4. So how do we put these other two? It's the same way it was last time. Up and down still matters more than left and right. Arsenic's further up. Tellurium's further right. What matters more? Up and down. So arsenic gets to be the next most, and tellurium gets to be the next to the least. Okay. A word about electronegativity. The noble gases here, they do have ionization energy, but they do not have, as far as electronegativity is concerned, it is not applicable. So in terms of that, it's Na. Because they already have all of the electrons that they want. We'll understand this a little bit more in the next module, but they do not want to attract more electrons to themselves. This is why they're snooty and called noble, because they don't want other people's stuff. They don't need it. So if you are asked for the most electronegative element on the entire periodic table, that, my friends, would be fluorine. Do not fall for it and say helium. Do not name anything from the noble gases. Fluorine is the most electronegative. Now, helium and neon and argon and the rest of them, they do have ionization energy. So, don't mess that part up. Now let's talk about why. Okay, we have been talking about further down, further left, but there are some reasons for the trends. And there's really two main reasons. Nuclear charge is the first one. It says the attraction of the positively charged nucleus to negatively charged electrons. Y'all should know that opposites attract. Positives and negatives love each other. So as you go across a period, we're talking from left to right, the atomic number increases. So we can go back here and look and see that this is true. As you go from left to right, the atomic number gets bigger, right? You go 19, 20, 21, 22, 23, 24, gets bigger the whole way. Well, what that means is that the number of protons gets to be bigger in the nucleus, but the number of electrons gets bigger in the electron cloud. And the more you have of each of them, the greater the attraction that you're having. So, in other words, go back here, if I go from potassium to iron, potassium has 19 protons and 19 electrons. Iron has 26 protons and 26 electrons. So iron is much more attracted to itself. So I think of this kind of like wearing a belt, or if you know what a girdle is, like women used to wear girdles that would like cinch their waist in to make them ridiculously small. So it's just kind of squishing things in and making it more compact. And as you go to another one, you now go to 27 protons and 27 electrons. So you cinch the belt a little tighter. And you go to 28 protons and electrons, you cinch the belt a little tighter. You get the idea? You just keep making the attraction greater and greater across the period to the right. So in other words, the electrons are being added to the same energy level all the way across a period. Let's mull that one over for just a second. Okay, remember when we did our electron configurations, we said that the row that you were in, someday I'll get an eraser here, the row that you were in referred to the number of energy levels. So if you're in the first row, you have 1 energy level. If you're in the second, you have 2, 3, 4, 5, 6, and 7. So if we work our way across the 4th row, like we just did for our example, when I'm adding another electron and another proton and one more of each and one more of each and one more of each, I'm adding them all no further away than the 4th energy level. But when I go from like potassium right here down to rubidium, I'm adding more electrons. Most of them are going into the same row, but then I add them to another energy level after I get to the 37th electron. It goes into an energy level that's further away. And if I go all the way down to this one, then it's got one more energy level. So what I'm trying to tell you here is that basically when you are doing with sizes, it says that they get bigger down a group because you have more energy levels, so the charges are farther apart. And so like it's hard to tighten the belt. And it's bigger to the left because there's fewer opposite charges. So like for potassium, we only had 19 of each, whereas like iron was further to the right and it had more positive and negative charges, so the attraction was greater. For ionization and electronegativity, well, the reason that they're greater up and to the right is because the atoms are drawn in much more because their size is so much smaller. They have a much greater hold on those electrons. All right. Now, as you go down the group, that is called nuclear shielding. So where we were just talking about adding an extra energy level as you go down each row, those extra energy levels cause shielding. It's like blocking it. If you've ever put magnets or something between your hands, as you increase the distance between the magnets, the less they can attract each other. And it finally gets to the point where they really don't have any influence on each other at all because they're too far away. And that's basically what's happening with the atom, is if you have the nucleus right here and one energy level, and then another one, and then another one, and another one, like as you keep going further and further out, the nucleus is still right here in the center. You're putting more protons here in the middle, but you're putting electrons further and further away. That is a really bad atom. So in terms of the size trends, you could say that atoms are bigger down the group, like we just said, because they have more energy levels, they have more shielding. And ionization and electronegativity are smaller where they're smaller because they have less shielding. So if we go back to this one and look at fluorine right here, fluorine has only 9 protons and 9 electrons. They're in the first and second energy levels. So they are really, really, like those electrons are really close to the nucleus. So they're really attracted and they are held on for dear life. And because they're being held on to so much, there's so much nuclear charge and so little nuclear shielding, fluorine is a teeny tiny atom with a great amount of ionization energy and electronegativity. On the flip side of this is francium. Francium is one of your largest elements. I think it is the largest element. And it's the largest element because it has 7 energy levels. So it has a fair number of protons and electrons, though not as many as some down this way. But they can't be held onto very tight because it's got 7 layers. So 7 layers and held on loosely makes it a large atom, and it also makes it pretty easy to pick off an electron, which gives it a low ionization energy. And since you can take electrons away, it really doesn't attract them to itself very well at all either. I mean, why are you going to draw something to yourself that you easily give up? So size and ionization energy and electronegativity, they all go hand in hand. I need you to probably play this back a couple of times to try to make sense of the ionization and electronegativity and the atomic size reasonings with this nuclear charge and shielding. I need you to be able to explain where nuclear charge is more and where it's less, and where shielding is more and where it's less, and understand what dominates the groups and the rows. The biggest player within a group is the shielding, because as you move down the group, you have more levels. And the biggest player in the periods is nuclear charge, is whether you have a little attraction or a lot of attraction. Okay, I have some practice problems for you. I have a feeling that this is probably going to be a good web conference conversation when it comes to office hours. So if you have questions, for the love of chemistry, please join me during the office hours. You can also post your questions in the Q&A spot, and I will do my best to answer them there.